Why connectivity on trains is so poor. Most of us have experienced this. You are sitting on a train, your phone shows that it has mobile signal or perhaps even 5G, but web pages refuse to load, calls break up, and messages remain stuck sending. You switch to the train's Wi-Fi, but that may be no better. It connects successfully, yet there is little or no usable internet. In this video, we will explain why providing reliable connectivity on a moving train is much more difficult than it first appears. We will look at the coverage, the train itself, mobility, congestion, and onboard equipment. More importantly, we will look at the different solutions and why no single technology can fix the complete problem. From the passenger's perspective, the symptoms are familiar. A video starts buffering, a Teams or Zoom call freezes, an audio call drops just as the train enters a cutting, a photograph takes minutes to load, the Wi-Fi symbol appears, but the internet does not work. These failures are particularly frustrating because connectivity may work perfectly for a few minutes and then suddenly disappear. This inconsistency is often worse than having no service at all. Passengers begin a task expecting the connection to remain available, but the network conditions change continuously as the train moves. It is also important to recognize that the problem is not always poor download speed. High latency, packet loss, failed handovers, and brief interruptions can make an otherwise reasonable connection feel unusable. There are two main ways that passengers connect. The first is direct mobile connectivity. The passenger's phone communicates through the train body or window with a mobile base station outside. The traffic then travels through the operator's network to the internet. The second is onboard Wi-Fi. Here, the passenger's device connects to a Wi-Fi access point inside the carriage. The traffic passes through an onboard gateway, then through roof-mounted antennas to an external mobile or trackside network. The distinction is important. Train Wi-Fi is not normally an independent broadband connection. It usually relies on many of the same mobile networks that passengers are struggling to reach directly. A strong Wi-Fi signal inside the carriage therefore tells us very little about the quality of the connection between the train and the internet. A train combines almost every condition that makes wireless communications difficult. It is a large metal structure traveling at high speed. It moves through multiple mobile cells and frequently passes through rural areas, tunnels, cuttings, forests, and built-up locations. Inside the train, hundreds of passengers may be using their devices at the same time. The radio signal must penetrate the carriage, while phones with small antennas and limited transmit power must send signals back out. The network must also maintain sessions as devices move between cells, frequency bands, and sometimes between 4G and 5G. Individually, each of these challenges can be managed. The difficulty is that they often occur together, creating a continuously changing end-to-end communications environment. Mobile networks are generally planned around where people live, work, and travel. That usually means towns, cities, business districts, and major roads. Railway lines do not follow those areas. They may cross open countryside, forests, valleys, or low-demand regions where there is limited commercial justification for dense mobile infrastructure. As a result, a train may travel along the outer edges of several mobile cells rather than through the center of a deliberately planned coverage layer. A network coverage map may show the general area has service, but this does not guarantee a strong or usable signal inside the train. Railways are linear corridors, and continuous service along a line requires a different planning approach from providing broad population coverage. Even where the outdoor signal is good, it still has to reach the passenger inside. A train contains metal bodywork, insulation, structural materials, and energy-efficient glazing. Together, these can significantly attenuate radio signals. This is known as vehicle penetration loss. The network may be able to deliver a strong signal to the outside of the carriage, but by the time that signal passes through the train body or window, it may be much weaker. The passenger's device then has to communicate using a small internal antenna, often while being held close to the body or surrounded by other passengers. This is why external coverage measurements and conventional mobile coverage maps do not always reflect the experience inside a train. Coverage outside the train is not the same as coverage inside it. Modern train windows are designed to improve thermal efficiency and passenger comfort. Many use low emissivity or low E coatings containing very thin metallic layers. These coatings help control infrared radiation and heat transfer, but they can also reflect or observe radio frequency energy. The result is that a window performs very well thermally, but may perform very badly from a mobile connectivity perspective. Only a reduced portion of the outdoor signal reaches the carriage. This can result in lower signal strength, slower data rates, greater latency variation, and more frequent reconnections. The problem is therefore not only the distance between the train and the base station, it is also the material through which the signal must travel. Modern sealed rolling stock can attenuate signals much more severely than older trains with simpler windows and construction. A moving train passes through a succession of mobile cells. The phone or onboard gateway must continuously measure nearby cells, compare signal quality, and decide when to move the connection from one cell to the next. This is known as handover. At high speed, these handovers occur frequently. The device spends less time in each cell, and radio conditions may change significantly between the measurement and actual handover. At cell edges, signals are weaker and interference from neighboring cells may be higher. If the handover is late, unsuccessful, or interrupted, data can briefly stall. A short interruption may seem unimportant, but it can freeze a video call, cause an application to time out, or interrupt a voice conversation. A long journey can include dozens or even hundreds of these transitions. The physical railway environment creates another set of difficulties. In a cutting, the track sits below the surrounding ground. The earth and rock can block the line of sight between the train and nearby mobile sites. Hills, forests, and buildings can create radio shadow zones. Bridges and viaducts can expose the train to several competing cells. Tunnels may block outdoor mobile signals almost completely. Long tunnels generally require dedicated infrastructure such as distributed antenna systems, leaky feed cables, repeaters, or small cells. The transition between outdoor coverage and a tunnel system must also be carefully managed, otherwise the connection may fail as the train enters or leaves the tunnel. Again, a general outdoor coverage map may not reveal these local railway-specific problems. A train can bring hundreds of connected devices into a mobile cell almost simultaneously. These passengers may be streaming video, downloading files, browsing the web, using social media, or joining work calls. The same cell may also serve a station, nearby houses, businesses, vehicles on surrounding roads, and another train traveling in the opposite direction. Mobile capacity is shared. It is not reserved for the train simply because the train has entered the cell. During peak travel periods, the sudden concentration of users can push a cell towards its limits. Speeds fall, latency rises, and applications begin to struggle. This is one reason the connection may work reasonably well on a quiet midday service, but become almost unusable on a crowded commuter train using the exact same route and infrastructure. It is possible for the base station to reach the train while the passenger's phone struggles to transmit back. The mobile base station has relatively high transmit power, large antennas, and sophisticated radio processing. A smartphone has limited power and a very small internal antenna. The return signal must pass out through the same carriage body and coated windows that weaken the downlink signal coming in. Fast movement also changes the radio conditions continuously. This asymmetry particularly affects applications that need reliable uplink, including video calls, voice over IP, file uploads, cloud applications, and sharing photographs. A passenger may therefore see reasonable download performance while their outgoing video freezes or a file refuses to upload. Good downlink performance does not automatically mean good overall connectivity. Download speed is only one measure of network performance. Packets can be delayed, lost, or retransmitted. A handover can cause a brief stall. Congestion can create queues in the radio network or backhaul. An application may eventually give up and time out. This produces symptoms such as frozen video, voice dropouts, slow loading web pages, and messages that remain stuck sending. Latency is especially important for interactive applications. A connection may have enough throughput to stream data once the transfer begins, but a slow or inconsistent response can make browsing and calls feel broken. The recent Ofcom measurement study found that latency was frequently the deciding factor preventing a test from meeting its overall good performance threshold, even where download and upload rates were adequate. Two recent studies show both the scale of the problem and the enormous variation between railway systems. The Ofcom Commission study measured 50 journeys across 24 rail lines in Great Britain. Its good performance threshold required at least 5 megabits per second download, 1.5 megabits per second upload, and latency of 50 milliseconds or better in the same test cycle. The best mobile network met that threshold 42% of the time. Onboard Wi-Fi met it only 1% of the time. Ookla's wider comparison of train Wi-Fi across Europe and Asia found even greater variation. Sweden achieved a median download speed of 64.58 megabits per second, compared with 29.79 in Switzerland, 1.09 in the UK, and just 0.41 in the Netherlands. The difference between the strongest and weakest markets was up to 158 times. The challenges are global, but the poor outcomes are not inevitable. Inside the carriage, the Wi-Fi connection may be perfectly strong. However, all passenger traffic still has to pass through the onboard gateway and the train's external backhaul. If that external connection is weak or congested, improving the Wi-Fi access points alone will not solve the problem. There are also legacy equipment issues. Across the European market studied by Ookla, nearly 2 in 5 train Wi-Fi connections still used Wi-Fi 4, and around 22% used the more congested and interference-prone 2.4 GHz band. Moving to 5 GHz and newer Wi-Fi generations can improve the in-carriage connection. However, Ookla found that countries with relatively modern Wi-Fi could still perform poorly. The conclusion is clear. Better train Wi-Fi requires both modern onboard Wi-Fi and much stronger train-to-network capacity. 5G can certainly help. It can provide more spectrum, greater capacity, improved latency, better beam management, and more efficient radio technologies. The Ofcom study found a significant improvement where 5G standalone was available. However, 5G coverage was not continuously available along many routes. The 5G symbol on a passenger's phone does not guarantee that the complete connectivity chain is working well. The railway still needs continuous outdoor coverage. The signal still has to enter the carriage. Hundreds of users may still share available capacity. Handovers still occur. The onboard gateway backhaul and core networks still matter. 5G is therefore an important part of the solution, but it cannot compensate for missing sites, severe carriage attenuation, inadequate backhaul, or poorly designed onboard systems. The first solution is to move from incidental coverage to railway-specific coverage. Incidental coverage is created when a mobile network designed for towns, roads, and businesses happens to reach a nearby railway. The train may receive some service, but the route was not the primary design target. Railway-specific optimization means aiming antenna sectors along the track, adding sites near known gaps, using lower frequency spectrum for reach and penetration, and adding capacity where stations and trains created concentrated demand. Policy can also play a role. Coverage and capacity obligations for important rail corridors can be included in spectrum licenses or supported through targeted public funding. Sweden has used rail-related spectrum obligations, targeted assistance, and access to railway infrastructure as part of its improvement strategy. Reliable connectivity starts with a strong and continuous outdoor radio layer designed for the route. Where improving the conventional macro network is not enough, a dedicated trackside network can be built. This uses closely spaced sites along the railway, directional antennas aimed towards the trains, and high-capacity fiber or microwave backhaul. Because the infrastructure is designed specifically for the route, coverage and capacity may become more predictable. Tunnel systems can be engineered as part of the same network, and handovers can be planned for the speed and direction of the trains. There are several real-world examples. France introduced dedicated coverage on flagship TGV corridors, initially targeting site spacing of around 2 to 3 kilometers. Austria has deployed hundreds of sites across approximately 1,500 kilometers of track. Japan has used dedicated systems to provide multi-operator coverage throughout Shinkansen tunnels. Trackside networks shift the design focus from nearby communities to the railway itself. Instead of requiring every passenger's phone to communicate independently through the carriage shell, the train can become the communications platform. High-performance roof antennas are positioned outside the metal body where they can capture a much stronger signal. Modern systems can use multi-band 4x4 MIMO or higher active rooftop antennas and power over Ethernet. Moving radio components closer to the antenna can reduce the losses associated with long coaxial cable runs. An onboard gateway can connect to several mobile operators, aggregate the available capacity, and switch between networks as radio conditions change. Ideally, those operators should provide genuine infrastructure diversity. 3 operator brands may not deliver 3 independent connections if they share the same underlying radio network. The train then distributes connectivity internally through Wi-Fi or another onboard system. Another approach is to improve the ability of radio signals to enter the train directly. Fine patterns can be removed from the metallic coating of low E windows using laser treatment. These patterns create paths through which mobile frequency signals can pass more easily while retaining much of the window's thermal performance. Tests cited by Ookla reported losses of approximately 20 to 30 decibels from conventional coated train windows. Research has shown that appropriately treated windows can perform much closer to ordinary glass. This is now being deployed at scale. Deutsche Bahn announced a program covering around 70,000 windows across 3,300 ICE and intercity carriages. The solution is passive. It does not need an amplifier and can support passengers connecting directly to different mobile operators. However, it only improves signal entry. It cannot create coverage or capacity where the outdoor network is poor. Active radio systems can also bring mobile coverage into the carriage. A repeater receives the outdoor signal through a donor antenna, amplifies it, and distributes it through service antennas inside the train. A distributed antenna system, or DAS, uses a network of antennas throughout the train to provide more consistent coverage across multiple carriages. An onboard small cell goes further by creating a local cellular radio environment inside the train, with the traffic carried through the train's external backhaul. These approaches can reduce the effect of carriage penetration loss and improve voice and data continuity. However, they require careful engineering. They must support the relevant operators and frequency bands, control interference, and manage gain correctly. Small cells also need appropriate coordination with the mobile networks and the train's backhaul system. The goal is not simply a stronger signal, but a controlled in-train radio environment. RF-permeable windows and repeaters can each improve connectivity, but combining them changes the radio design. A repeater relies on isolation between the donor antenna outside the train and the service antennas inside. With conventional metallic windows, much of the repeated indoor signal remains contained within the carriage. When the windows become radio transparent, more of that amplified signal may escape. It can then couple back into the external donor antenna, pass through the repeater again, and create a feedback loop. If the isolation becomes too low relative to the repeater gain, the system may become unstable or oscillate. It may increase uplink noise, automatically reduce its gain, or produce inconsistent indoor coverage. This does not mean that the technologies cannot coexist. It means that the Windows donor antenna, internal antennas, and repeater gain must be engineered and tested as one RF system. A high-quality train Wi-Fi system should combine several complementary train-to-ground links. These may include 2 or more independent 4G and 5G operators, a dedicated trackside network, station or depot connectivity, and increasingly low Earth orbit satellite backhaul. The onboard gateway can intelligently bond or switch between these connections, selecting the best available path as conditions change. LEO satellite is particularly useful on rural, coastal, or lightly served routes. However, it is not a universal replacement for terrestrial networks. Tunnels, deep cuttings, buildings, and vegetation can obstruct the view of the sky. Rail-certified terminals must also meet requirements for vibration, weather protection, power, and electromagnetic compatibility. The likely end state is therefore hybrid. Cellular, trackside, and satellite links work together, supported by modern Wi-Fi access points throughout the train. Connectivity should be designed into new trains rather than added as an afterthought. A connectivity-ready train can include RF-permeable windows, built-in roof antenna mounts, cabling, power, cooling, and reserved space for gateways and future upgrades. It should also support multiple operators and allow equipment to be replaced as technologies evolve. However, train design is only one part of the problem. The train operator, rail infrastructure owner, rolling stock manufacturer, mobile operators, connectivity suppliers, regulators, and government all control different parts of the system. Railway infrastructure owners may need to provide access to sites, fiber, and power. Governments and regulators may provide funding or establish spectrum coverage obligations. Commercial responsibilities and service level expectations must also be clear. Retrofitting later is harder and more expensive. The train, trackside, network, policy framework, and commercial model should be designed as one system. So, why is connectivity on trains so poor? It is not because one technology has failed. Reliable connectivity depends on the complete chain. There must be strong coverage along the rail corridor. The signal must enter the carriage or be captured by external antennas. Connectivity must be distributed properly inside the train. The backhaul must have enough capacity. Handovers must work at speed. Congestion must be managed, and the organizations involved must agree on ownership, funding, and performance. A weakness at any one of these stages can undermine the entire passenger experience. The solution is therefore not simply more 5G, newer Wi-Fi, satellite repeaters, or laser-treated windows. It is a coordinated system combining the trackside network, rolling stock design, onboard equipment, multiple backhaul technologies, and commercial alignment. For anyone interested in learning more about these technologies and the work being done to improve connectivity on trains, TrainComms 2026 takes place in London on the 18th and 19th of November. The conference brings together train operators, rail infrastructure organizations, mobile and satellite companies, connectivity specialists, equipment suppliers, and policy makers. Topics include onboard Wi-Fi, mobile coverage, dedicated trackside networks, multi-link backhaul, satellite connectivity, and the passenger experience. Improving rail connectivity requires cooperation across all of these organizations, which is why specialist events such as TrainComms are valuable. You can find more details at traincoms.com. Thank you for watching. If you found this video useful, please like the video, subscribe to the channel, and check the links in the description for additional resources. We hope to see you again soon. Goodbye.